So, sir, I think we should start.
Yeah.
So, students, participants will be joining slowly. Already
Okay.
12 participants have joined. So, welcome back to the fundamentals of quantum computing. So, this is the eighth session, and today's second session. We have with us Dr. Sudhendu Vikas Mondal. So, let me introduce him. Dr. Sudhendu Vikas Mondal is working as a quantum software engineer at TCG Crest, Kolkata. He is also an IBM certified associate developer in Qiskit. His areas of interest are ternary quantum circuits and ternary quantum algorithm. So as Dr. Mondal said, like you'll be having real experimental showing opportunity of showing the experimental setup along with how to write codes, mainly Qiskit, which is very popular, and the people who are bit knowledge of quantum computing and related thing, they know that Qiskit is very popular, which has been developed by IBM for writing codes, implementing quantum algorithms and all. So we have a good opportunity to learn that and see that. So thank you, sir. Thank you for joining, giving
Okay.
your valuable time. So please start your session.
Okay. First of all, I would like to thanks the organizer and special thanks to Dr. Samaprasad Mukherjee and Professor Amlan Chakraborty to give this opportunity. Okay. So I'm sharing. Oh, I think I missed something. Should I need to start broadcast or I am not very familiar with him?
You have any sharing option?
Yeah, I have got this sharing option, but after doing this, it asking start broadcast or something like that. Should I?
So there is no option for sharing your screen or sharing window.
No, just I'm rechecking. Uh, Share screen. And when I'm clicking share screen, it comes screen broadcast.
So do that. Actually, nobody asked. I also don't know because we are having
Yeah.
dedicated application for that.
Hmm.
When you are broadcasting, your screen was
Just
showing actually.
showing. Okay,
Yes,
okay.
that time it came.
Now?
Yes. You start your PPT. Let us
Okay.
show.
Hmm.
Yes, your screen is coming.
Okay, fine. Just
Yes.
no, it's coming.
Yes. It is visible.
Okay, that's good. So I think participant already go through the some previous session where they able to understand what is quantum computing and what is the motivation of this quantum computing. They have already heard from the previous lecture from Professor Amlan Chakraborty and Dr. Amit Shah and Dr. Shoikat Basu also present in last session. I think he also told the what is very basics of quantum computing from before going to the quantum error correction and his some research work. And in my today's talk, I will not say any research component or research work, but I try to give you some observation of quantum computing, how to implement. Suppose I have some expression or some mathematical expression. How can you cook it into a quantum computer? It is not a easy task in now still nowadays. Still we have no enough rich compiler or interpreted like this. Just we writing some mathematical expression, it automatically comes to the quantum circuit or something like that. There are, but still they are not enough reach to do all type of expression. So I actually changed my thought after listening the Shoykot's talk. So I really not want to go through this all slides of I have prepared. Uh, in my talk, I try to describe the quantum Fourier transform algorithm and to how can we convert this quantum Fourier transform expression to a quantum circuit. I'll describe it. And to understand this, we need to know little bit about the some ingredients of this quantum circuits and how it's used in quantum circuit. I will discuss these things. So before going to the just preliminary, I am saying what is quantum computing. You have already learned. Quantum computing actually obeys the quantum mechanics. I think you have already gone through some lecture session of quantum mechanics, so you have enough idea what is the quantum mechanics law and what is the different quantum mechanical principle. So I'm not describing this, but try to understand classical computing is quite different from this quantum computing, because classical computing is always over the law of classical physics or classical mechanics, but quantum computing actually maintain or over the law of quantum mechanical principle. And what is the what are the advantage you have already learned. So I'm not describing the motivation. I think all of you are enough motivated by the Professor Amlan Chakraborty and others speaker, that what is the need of quantum computation in present scenario, how to solve the hard problem. And to solve the hard problem in classical computer really difficult tasks, and some problem we can't solve really. Yeah, so we need some quantum computation for solving this hard problem. Like Shoykot already in last session, Shoykot says that Peter Shor's algorithm is very difficult to implement in classical computer. Uh, and also Peter Shor's algorithm is completely a fault-tolerant quantum algorithms. By first, it shows the advantage of using the quantum computer, because we can factor the uh, uh, equation and something. So again, it comes to the what are the basic building block of quantum computer. Again, it's qubit. All of you know what is qubit, but still I try to give you the some analogical idea. Suppose in our classical computing, we know uh, actual building blocks of classical computer is classical bit 0 or 1. And if I show something, if analogically, suppose this red pen is our bit 0 and this white pen is bit 1 in classical computing, and these two things are completely deterministic. We can mimic it by using some voltage level, ground zero could be as your zero state, and 5 voltage can be represent as a 1 state. But in quantum computer, qubit is quite different. Analogical concept, uh, because you all of you already know that quantum computing is a probabilistic computing. Qubit is a probabilistic uh, bit, and it can be in superposition state. I think all of you are this name superposition last few of days. So what is that case? Suppose I have a box. If I put any pen over there, and if I ask what is the state of this system, so you can answer it. you can't answer deterministically the red pen is there or white pen is there, but you can say there is a 50% chance to a red pen and 50% chance to our white pen. Okay, and all of you know those Shannon's theorem, and Shannon says that information content is complete in uncertain condition. Its entropy is very high. In deterministic, say suppose if I say sun is arising east every day, this is the obvious case. So its information content is very less. So in this concept, qubit contains, because qubit is a probabilistic, it's an uncertain condition. There is a equal probability of they are existing in red pen or white pen. So it contains more information there. So our challenge is to encode the real life problem. How can we use this information to encode our real life problem? This is the challenge in quantum computer, because it's a probabilistic. But as a real life people, we are aware of the deterministic computing. So we compute or encode a real life problem to this probabilistic space and compute over there, and then we get back our result into a deterministic space. So how can we actually, you have heard some measurement thinking. What is that mean measurement? Measurement means if I open this box, then I can determine that there is a red pen. So this is actually a measurement. Now there is no quantum phenomenon, and we actually destroy the quantum state after this measurement. And to confident about this quantum state, we need to repetitive measurement, so that we can after this some statistical analysis, we can say okay, that was the state. If I measure one times, we can't say that confidently this was our state. Okay, this is the philosophical background of the qubit, and we will use this qubit for computing our some real life problem. Okay, fine. And also, you know, this superposition principle, I'm not talking about it. Actually, I'll not bore you to repetitively saying that. And physical representation of uh, qubit, there is a so many technique to generate the qubit system, like a superconducting qubit, neutral atoms qubit, photonic qubit. There are so many things. They have a different uh, criteria to design a qubit, and also said that different mechanism. And popular still nowadays, still popular is superconducting and neutral atom qubit, as last talk Shoika says. uh, and analogically, you can think about this hydrogen atom case. There is a two orbital, and in the lower state is actually our zero state, and outer orbital is one state. There may be in and also qubit can stay in a superposition state also. Okay. And in case of, I'm talking about some example of this qubit, but I'm not a physicist, so I can't able to say the deeper observation of how to prepare a qubit. But I can say in our experimental lab, where you in our office there is an experimental setup of superconducting qubit. In last I will show some picture of this lab. And in case of superconducting qubit, actually we try to put our one atom in a some oscillator, you can say. I'm not talking about the deep thinking, but I can say in an oscillator. But actually oscillator is in nature, it is a harmonic oscillator. Okay, sorry about my drawing. And so harmonic after each and every level is fixed of length. So it is difficult to bind on some atom into a, or segregate the state. Suppose if I say this is a state 0 and this is a state our 1, but it is very difficult to stay the if it is a equally distance of this each and every step. So it's very difficult to stay or read out this 0 state to 1 state. That will be very difficult. Suppose if we represent classical bit 0 as 5 voltage and 1 is also some same level of voltage, it will be very difficult to encode or decode. That's why we need a different kind of oscillator, and this is called anharmonic oscillator. In this anharmonic oscillator, level is not equally separated. There is a distance maybe like this. So we can enough segregate it between the 0 and 1 in case of enharmonics. To make this enharmonic oscillator, we use some LR circuit with some capacitor and some resistance. We will add with we actually added with this circuit. In this way, we prepare this, and to preserve this qubit, we required a refrigerator. I'll show this already show a source, but I will show in my lab's refrigerator. And this is the one way to implement the qubit uh, in superconducting technology. And you think that to make this quantum computer, actually we need, along with the physicist, we need a very good electronics engineer, because we in upper level we see the quantum gates, but this quantum gates is actually different kind of pulse, microwave pulse. You see in this picture we send some microwave pulse. By using this microwave pulse, actually we ignite the state, or change the phase of this qubit in anharmonic oscillator. So design this pulse, we have required so many electronics engineer, because there is some FPGA toolbox. From this FPGA toolbox we generate some uh, signals with a different frequencies, and we need some amplitude modulation, because signal is generated in low frequency. But to changing the state of the qubit, we required a high frequency, so we need to convert it into gigahertz frequency. So we need some mixer toolbox. By using this mixing toolbox, we enhance the signal. And also to implement the superconductor, we need to taking care about the very fine tune of this microwave signal, because now still struggling this quantum computing world to make a very fine tune of this pulse, because this pulse can interact with the environment, so that we think we are giving this amount of pulse to the qubit, but when it interact with environment may not go to the exact pulse to the qubit. Because see, yeah, our FPGA toolbox cannot work in a sub-zero temperature. It should be worked in a different temperature, but we need to preserve our qubit in a sub-zero temperature. So we need two separate. Within this refrigerator, we actually put our qubit or anharmonic oscillation, and pulse toolbox is completely outside from the refrigerator. We need some big cable to transfer this signal. Within this cable, when we send these microwave pulses, it will interact with the environment. So it is very difficult to send the accurate pulse to this, and that's why it's come some noise. And also, not in the accurate pulse, we need to reduce the timing. If timing is very high, transmission timing is high, then qubit automatically decoher, and this type of noise will come into the system. And this is the challenge in still now, how to make a very good pure qubit. This is the challenge. And so many teams, IBMs or others team also working with that, how to we can overcome this situation. Okay, this is the really all of this qubit, but I have no enough idea of the trap ion technology, because I never visit this Traptine lab, in our lab there is also another qubit we are preparing. This is a photonics qubit, but it is not will not use this photonic qubit for a quantum actually computing of algorithm or like that, because photonic qubit only generate the Gaussian state, not but it will not prepare the non-Gaussian state. Still now another company Xanadu also try to prepare non-Gaussian state or something like that without the Gaussian state, and uh, we are not able to design some quantum algorithm. Still this is challenge, but photonic qubit may be used for quantum communication. And because photonics by nature is linear computing, but we required a non-linear state. But it is possible to design a non-linear state, but still it is challenging. That's why in our lab we use photonic qubit for a quantum communication or quantum sensing. And I have no enough idea about this photonic qubit. Still I'm working with a experimental team with a superconducting team. So really hard to say any comment regarding the photonic qubits. Now come to the mathematical model of qubit. I will not describe here. I will not take much more time to describe the mathematical model. Qubit have a uh, one pure state is 0 and 1, and it belongs to the Hilbert space. From the your quantum mechanics lecture, you know this what is Hilbert space and how can represent mathematically to any component in Hilbert space. Actually, qubit can show mathematically write in a Kate notation or Bra notation, and this each and every Kate vector you can write in a, matrix column matrix representation. That's why 0 qubit is represented here 1 0 and 1 is 0 1. And this is another qubit mathematical model. In general qubit, you can write in this way: psi alpha 0 and beta 1, where alpha and beta are complex number. And there is another very condition is alpha 0 plus beta mod of alpha square plus mod of beta square should be 1. This is a very good condition for becoming a qubit. We can and this is called a pure qubit, pure state, not a mixed state. We are not talking about the mixed state. And pure state, this condition should be there. And in quantum computing, other than this qubit, we need some operator. I will describe this operator in details. For this operator, what is the role of this operator? Actually, role of this operator, if I apply this, suppose U is some quantum operator. If I apply over this psi, it will change the state of this psi, right? Psi dust. Okay, so it will change, or you can say it will after applying this quantum operator, our qubit will change its phase or its position, you can say. Fine. So I'm not describing rest of the. Let's directly goes to the uh, my talk. I'm very sorry to I'm not preparing any presentation. I'll describe by mathematically. See, I have already told you that there is a quantum operator. So there are some one qubit operator. You have already know the name. One is there is one qubit operator is sorry, and there will be the Pauli X operator and Pauli Y, Pauli Z, and there is another good operator. This is called Hadamard. What are these operator? Just like if I apply X operator over the state 0, it will generate 1. And if I apply over state 1, it will generate the state 0. And what is that meaning of this operator? Actually, we can write mathematically this X operator in this way, by a matrix form. Each and every 1 qubit, this is minded 1 qubit operator. Okay, this 1 qubit operator can be represented by a 2 cross 2 matrix. So we know the matrix represent of 0 state is 1 0 and 1 is 0 1. Okay, so how can we represent this X operator? So first column of this matrix represent the outcomes. If I apply the X operator over 0, what will be the state? State will be the 1. So what is the matrix of this 1? It is 0 1. And second column represents, if I apply this X operator over 1, what will be the outcomes? Outcome is 0. And what is the matrix of 0? Matrix of 0 is 1 0. And this is the matrix representation of X gate. Okay. Similarly, you can represent Y gate if we apply Y over 0. And what will be the outcomes? It will give you I1. And if you apply over 1, it will generate minus I0. So very easily you can design this matrix corresponding to this Y operator. It will be 0 I and minus I0. Fine. Next, if we apply Z gate over 0, it do nothings. It remains the same. And if we apply Z over 1, it will generate you minus 1. Again, I'm very sorry to my handwritten. So what will be the matrix? You can generate it like this: 1 0 0 minus 1. Next, if we apply Hadamard over 0, it will generate the state 1 by root 2 0 plus 1 by root 2 1. Fine. And if we apply this Hadamard over 1, it will generate 1 by root 2 0 minus. If we make this my tab in this way, it will be better for me. 1 by root 2 1. Fine. So what will be the matrix representation? Similar way, you can represent this matrix 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2. Okay. This is the first observation of 1 qubit gate. Now I want to say another thing. I have already shown in in my presentation. There is a shy state, and this is the generalized qubit, and we can represent it alpha 0 plus beta 1. And there is a condition: mod of alpha square plus mod of beta square should be 1. Always these conditions should be satisfied in quantum computing. And this is called a non-preserving condition. So we can design any operator, anything can be a quantum operator. quantum operator also should be a norm preserving operator, so that after the computation, if I apply something u over there, sorry, some operator, apply some operator of u of this psi, it will generate some other state, say alpha dash 0 plus beta dash 1, and here should be alpha dash mod square plus beta dash mod square should be also 1. So anything cannot be a quantum operator. There should be some condition to be a quantum operator. What is this condition? We need to find some operator which can preserve the norm of this qubit. So what will be the operator from your linear algebra course or from this first or two lecture? I think you have heard this name of this operator, type of this operator, not say name of this operator, type of this operator. This operator should be unitary in nature. And what is that meaning of unitary? You all of you know, U dagger should be U equal to the U inverse. So that this is the condition of any quantum operator should be a unitary. And this is why it is a non-preserving operator. You know, the from the your linear algebra course, this unitary operator, determinant of this unitary operator always 1. That's why unitary operator preserve the norms. And now you can visualize your qubit in analogically. Suppose we have a globe, and if I draw any point over this globe, each and every point can be a qubit, and globe taking as a unit sphere, so that its norm is unitary. So this is the one observation from this point. Any operator of quantum computing should be unitary, because we need to preserve the norms. Another observation from this unitary operator, actually, if we apply this unitary operator over any vector, it will generate a lambda psi, where this lambda is a eigenvalue of this unitary operator, and it's a special type of eigenvalue. It is like a e to the power I theta. It's a complex number, and special complex number, its magnitude should be 1. Okay. And third observation from this unitary operator, if unitary operator there two or more, for the case of single qubit gate, unitary operator is a 2 cross 2 matrix, so it has a 2 eigenvalues. Suppose it has a 2 eigenvalue. One is lambda a, another is lambda b. If these two are not equal, corresponding, then every eigenvalue corresponding as some eigenvector. I am writing eigen v, eigv. If these two are not equal, then these two eigenvectors should be orthogonal to each other. And orthogonality means there is no, it's a projection, 90-degree projection. Orthogonality, that means, suppose I'm giving you one example here. See, JET-GAT. Take the as an example of JET-GAT. If we apply Z over 0, it remains 0. If we apply Z over 1, it will be the minus 1. So what are the two eigenvalue corresponding to this? Here eigenvalue is 1, and here eigenvalue is minus 1. And these two eigenvalues are not equal. so that corresponding eigenvector 0 and 1, these two are orthogonal to each other. If we take the inner product between these two, 0 and 1, then it becomes 0. How? See, hmm, what is the matrix representation of 0? We know it is 1, 0. If I take the bra, it's a complex conjugate transpose. So it will transpose to the row vector 1, 0. So we can take 1, 0 multiplication with 0, 1. So it becomes 0. So it is a orthogonal state. And this orthogonal state can be used as a orthogonal, can be used as a computational basis. That's why in quantum computing, there is a computational basis called 0 and 1 state. They are orthogonal to each other, and this computational basis is actually eigenspaces of our Z operator. And if we apply this Z operator over this any qubit, it's actually rotate over the Z axis. And there is another basis state. Suppose I have already shown you the Hadamard case. If I apply this Hadamard over this 0, it will generate 1 by root 2 0 plus 1 by root 2 1. And if I apply it to 1, it will generate 1 by root 2 0 minus 1 by root 2 1. And see, from here directly we can say the what is the eigenvalue of this thing, because actually this state is called a plus state and this is called a minus state. These two are a eigenspace of X state or Pauli X operator. This is the eigenspace. And if you compute that inner product between this plus and minus, you will also get the 0. You can easily compute it in yourself. You can see that inner product will. So these two are also orthogonal state. Actually, pictorially, if I mm, draw first, if it is a unit sphere, then there is a computational basis 0 and obviously opposite direction. This is a 1. But this computational basis exists in a equator of this. If I say this is a plus state, then opposite will be our minus state. Okay. And there is a very interesting properties between these two bases. This is the eigenspace Z basis and another, not a basis, we can say, yeah, we can say basis. And there is another basis from a basis state. This is plus minus 1. This is the eigenspace basis of X. There is some interesting features between these two basis set. I try to give this observation to you. Okay. In case of, I have already shown you there. Take the different color. Take. Oh, sorry. I take two operator. One is Z operator and I'm taking X operator. These two are very interesting operator because they two are two different forms. Their eigen space actually forms two different basis state, and that's why they make some interesting properties. Okay, see, if I taking considering about the computation basis 0 1, and I'm taking another basis there plus and minus. Actually, this concept is required to understand the quantum Fourier transform. That's why I'm explaining. I think you have already know these things, but again, I'm just telling you. So in computational basis 0, 1, you know, after my description of quantum Fourier transform, you have understand what is this basis state. Still now, I am not saying what is this basis state. I am saying this one is computational basis state. I am saying this one is other. I will say what is the meaning of this other this basis state. I will say when I will talk about the quantum Fourier transform. Okay, so there is a, if I apply this z over 0, again I am talking this very, it will be 0, and if I apply this, it will give you the 0 minus 1. And in this computational basis, x is working as a not gate or flip gate or flip operator, so it will give you the 1. See, from here I can get a eigenvalue straightforward just like a z, because z operator there is two eigenvalue. I can say this one is +1 and -1 because it's map the same eigenvector there. But here it will not map the same eigenvector 0 to 1, but this two vector is not same. That's why we can straightforward say that eigenvalue of this x is 1. And if I apply this one over there, it will give you 0. So here it is a not operator, and in computation is z gate act as a phase shifter. It will shift the phase only. Now coming to this point, if we working on this plus minus basis, what will happen if we apply the z operation over plus state? So write this plus state 1 by root 2 0 plus 1 by root 2 1. Now take 1 by root 2 z over 0 plus 1 by root 2 z over 1. So if I apply z over 0, it remains same. But if I apply z over this 1, it will goes minus 1 by root 2 1. So what is this state? This state I have already sent, this one. So it will change to the minus. Now again, if I apply z over minus state, I jump this step. If I apply the z over this 0, it will give you 1 by root 2 0. And if I apply z over this one, it will give minus, and then minus minus will be plus root 2 1. So what is this state? This state is actually a plus state. Just like this plus state is 1 by root 2 0 and 1. So here in this computational z act as a phase shifter, but in this computational basis z acting as a not operator, not a phase shift operator. Okay, but if I apply x over this computation basis plus, I'm jumping the step, so it will be 1 by root 2 1. If I apply x over 0, it will be the 1. If I apply x over 1, it will be the 0. So what is that state? This state remains same, plus. Now if I apply x over this minus, so if I apply 1 by root 2, 0 becomes 1 because we are applying x gate, and there will be minus 1 by root 2 0. If I take this minus over there, then it will be 1 by root 2 0 minus 1 by root 2 1. So what is this state? Actually, see, he in this basis, x gate act as a phase shift gate. So This is happening because this computational basis is a eigenspace basis of Z operator, and this basis is eigenspace of the our X operator. That's why rule is changes between these two different bases of Z and X. Okay. So this one is another observation, and I need another ingredients to describe the QFT. This is called a phase kickback. To describe this phase kickback, before that we need another 2 qubit operator. This is very important 2 qubit operator. This is called a C naught. By mathematically, we can express the C naught as tensor. I think all of you familiar with this tensor product, so I'm not telling this. And this is identity plus tensor with X. This one is X operator. This is the mathematical expression of our C naught gate. And from this mathematical expression, you very easily you can constitute this C naught gate. But by definition, what is C naught gate? Just I am drawing this picture. C naught gate is a 2 qubit gate. This one is called control, and this one is our said a target. And by definition, what is that? It will say not suppose this one is our A and this one is our B. It will act not B if A equal to sorry A equal to 1, and it is B otherwise. That is the definition. This is a mathematical expression of our C naught gate, and this one is our definition. So what does that mean? If control gate is 1, then NOT operation will act over this B. And nowadays in computer, in quantum computer, designing this CNOT gate, pure CNOT gate, actually designing is very difficult. Actually, this CNOT gate gives a more error to our circuit because there is a two different qubit and we need to make a coupling, and this coupling by using some wire is there, and because there is a two different pulse we have to give, and there, and also I forgot to say that in case of our qubit, we I have told you that if I measure the qubit it will destroy, but in real quantum computer there is a two different toolbox. Suppose for a particular one qubit there is a one enharmonic oscillator to actually preserve the qubit, and there is another harmonic oscillator. This is called a cavity, or this cavity is designed by a resonator. Actually this resonator is used to measure the any qubit. We will not disturb the qubit directly here. We actually measure the cavity in experimentally. By measuring the cavity, we try to understand what is the state of the qubit without destroying the state of the qubit. And this is done by some mechanism. I'm not saying telling this what is that mechanism. Actually, really, I don't know this experimental setup really good. Uh, so there is two, and why this CNOT gate gives more error? Because we need to couple this to enharmonic oscillator as well as to cavity or resonator. So there is so many interaction between the fridge where qubit is up, and outside of the fridge there is some other toolbox. We need to interact more. That's why there is some environmental interact is coming. So designing the pure 2-qubit gate still is challenging. So in our circuit, if there is more 2-qubit is there, so our circuit will be more error prone. That's why when we try to design a high level algorithm to a quantum circuit, our first target is to reduce the number of 2-qubit gate. And if you go to the IBM's site or IBM cloud, you will find the gate fidelity of 1-qubit gate almost 1. Uh, it's a 1, very negligible error. But you will find that any 2-qubit gate is there. There is only ECR 2-qubit gate. They are not now using a CNOT as a 2-qubit gate. They are using a ECR as a 2-qubit gate. But this get fidelity of this 2-qubit gate is very less, and now it is almost 99 or something. Another superconducting machine, there is a developed by Regedi. They have a 2-qubit gate fidelity is very less, 92 and 93. So if you went to the heavy loaded 2-qubit circuit to Regedi machine, you will not get a expected outcome. This is the challenge in real hardware. So come back to the again in our talk. There is a phase. Now I'm trying to describe the phase kickback. There to describe this phase kickback, we required this CNOT gate, and you understand what mathematical expression as well as the uh, mm, definition of CNOT gate. And matrix representation of this CNOT gate will be look like this. If we do computation over there, I'm not doing this whole computation this. If you do this outer product between this 0 and with this tensor product, then okay, let's do it. Then it will be clear for you. Oh, sorry. Let's 0 outer product with Z0. Uh, am I more? Yeah, actually, I'm more mathematical. Is it okay for you? Or I'm uh, actually um, um, I, I I don't want to bore you in this post lunch session, but I'm too mathematical. Is it okay? Or
Yes, sir. Yes, sir.
okay, that's fine. Thanks. So what is this outer product? Outer product, 0 0. How you can compute it very easily? Bracket condition. Okay, I'll show you. There is 1 0 and there is 1 0. If you do this computation, you will get this matrix. This is the dot cross product. And what is the outer product of 1 and 1? You will get 0 0 1 very easily, because 0 1 with 0 1. It's a 1 cross 2, and this is 2 cross 1, so it will be a 2 cross 2. Now directly come into this expression, tensor with identity and tensor with X gate. So matrices look like this: 0 0 0 1. Oh, sorry. 1 0 0 0, and tensor with identity matrix is 1 0 0 1. And here 0 0 0 1, and this X gate matrix, now from this tensor product, this one is 2 cross 2, this one is 2 cross 2, and 2 cross 2 and 2 cross 2. So after this tensor product, it will be a 4 cross 4 matrix, because tensor product makes a higher space. So if we do matrix 1 0 0 1, rest are 0 0, Now plus, so 0, 0, 0, 0. Now if we add, and it will come 0, 1, 1, 0. There is a C0 matrix. And I can say you another tricks. You don't need to do this computation, but directly you can generate this matrix for C0 gate. You can observe these things. Actually, this is a I 2 cross 2, then 0 to 2 cross 2. There will be a 0 2 cross 2, and there is a your X gate. There is the composition. Actually, you can design any control operator. Suppose if you want to design a control Hadamard gate, you will find it in Qiskit also. Control Hadamard. You no need to do the whole computation. You directly, very easily see what is the composition of this matrix. There is identity, and what is the dimension of Hadamard gate. This is a 2 cross 2 gate. So we need to put there 2 cross 2 identity, 2 cross 2 0, 2 cross 2 0, 2 cross 2 0, and here I put X because it is a control NOT gate. But it is, if you want to design control Hadamard, there will be 1 by root 2, 1 by root 2, root 2 minus 1 by root 2. So in this way, you can design any control operator if you need from the logical end. This is the expression. Okay. Now come to the phase kickback. Suppose I'm generating one kind of circuit. Okay. Okay. I'm generating a high level circuit. Okay. Suppose we are giving plus as an input, and here also I'm giving a minus as an input, and I'm putting here the C0 operation. So if we do the computation, what will happen? There is a plus state and minus state. It is actually plus tensor with minus. If I write everywhere this plus minus, that is actually meaning of plus tensor with this minus. If we put any qubit in vertically, that means their tensor, this is a tensor field. Each and everything's a tensor with it. Okay. Now, what is this scenario? 1 by root 2, 0 plus 1 by root 2, 1. Sorry, I think I missed something. Oh no. And 1 by root 2, 0 minus 1 by root 2, 1. Okay. Now, if I compute there, half of, there will be 0, 0. 0, 0 means 0 tensor with 0. 0, 1. Sorry, that will be the minus 0, 1 plus 1, 0 and minus 1, 1. Now we need to apply the C0 gate over there. C0 gate between these two. There is a control and this one is target. This one is control, this one is target. This one is control and this one is target. This one control and target. So if I apply this, 0, 0 remains same. Minus control is 0, target will remain same. Now control is 1, so target will be 1, 1. Now control is 1, so target will be 0, 1, 0. Fine. Now, oh sorry, there will be half. This is not a Now I want to take 1 by root 2 0 as a common. So what will be there? 1 by root 2 0 minus 1 by root 2 1 over there. And also here, if I want to take minus 1 by root 2 1 as a common, then we'll get 1 by root 2 0 minus 1 by root 2 1. So we have a state 1 by root 2 0 minus 1 by root 2 1, and tensor product worth 1 by root 2 0 minus 1 by root 2 1. So what is that state? State is minus and minus. See, we will start with a state plus minus, but after that we are getting a state minus minus. Actually, by composing the circuit, we transfer the phase to the control, not a target. See, control phase is minus there, and we transfer this phase to the control gate. That's why control bit. That's why it is called a phase kickback operator. Okay. I need this type of ingredients to start my QFT. I'm again really sorry, I'm little bit mathematic. Now come to the QFT. Obviously, you may ask question, why should we learn QFT? Actually, QFT is a basic building for block of so different algorithms. Like if you want to implement the Shor algorithm in real quantum computer, one component of the Shor algorithm is QFT, quantum Fourier transform, because in Shor algorithm we try to frame our Shor algorithm in a order finding algorithm. So find the order, we need to the estimate the phase. That is called a quantum phase estimation in another algorithm, which gives a exponential speed up than the classical computing. So to implement the QFT, we have again required the build as a small component. This one is QFT is required. So QFT is very important for a design different quantum algorithm, because it's a building block for so many algorithm which gives a exponential speed up. Okay. Uh, and one liner I can say QFT is a QFT operator is nothing but a basis changer operator. What is that meaning of this basis changer operator? Actually, QFT change the basis, change the state from one computational basis to a Fourier basis. What is that computational basis? I have already told you this computational basis is 0, 1. If we need to change this computational basis to a Fourier basis, then we need to use a QFT, quantum Fourier transform. What is the Fourier basis? One for 1 qubit case, I have already shown you, but I want to prove for 1 qubit case, this Fourier basis is actually plus and minus is our Fourier basis. How I will prove it when I derive this QFT. Okay, so take a one state X, any arbitrary state, and if I do the QFT, base should be, I'm writing this X bar or X dash. This is the QFT of X. Now I'm writing the mathematical expression of QFT is, okay, before that I want to say another thing. In case of 1 qubit, there is a computational basis is 0, 1, but if we take a 2 qubit state, then our computational basis will be 0, 0, 0, 1, 1, 0, and 1, 1. There is a 2 qubit case. computational basis becomes 0, 0, 0, 1, 1, 0, 1, 1. There is a 4 state. And in case of single qubit, there is 2 case. So for n qubit case, sorry, this is a small n qubit case, we have a 2 to the power n number of computation basis state. I take another variable, n is 2 to the power n. So if I apply QFT over this x, then our mathematical expression will be some normalization condition 1 by root over n summation of y equal to 0 to starting 0, that's why n minus 1. There will be e to the power am I connected? Okay, just is my skin is visible? Okay, okay. So this expression is 2 pi I x y n y. Okay, this is the mathematical expression. If you are familiar with some signal processing, then you will very easily know this expression. This is the inverse Fourier transform in case of our classical computing. So this one is the expression for our QFT. If we apply QFT over this X state, it will transfer the state into this state. That means X is in a computational basis and it transferred to the Y state. This one is our Fourier basis state. But if I ask, what will be the quantum circuit for corresponding this expression? We can't get any idea. We are not able to design. And see, I told you that in very first, still nowadays, we have no enough rich compiler just writing this expression and it will generate the quantum circuit. So we need to do some, if we want to implement this expression, we need to design our quantum circuit so that we can implement this expression. But viewing this expression, it is very difficult to digest or cook this expression to a quantum circuit. It is very difficult. So we need to rewrite this expression so that how we can design a quantum circuit, or we can get some intuition to how to design a quantum circuit. Let's start with an example. If we are talking about a 1 qubit case, then what will happen? What will be the expression? 1 qubit case means capital N equal to 2, because a small n equal to 1. So 2 to the power 1 is 2. So this expression becomes 1 by root over 2 and y equal to 0 to 1 e to the power 2 pi I x y y. Now if we expands this equation, so what will happen? 1 by root 2 for y equal to 0, it is e to the power 2 pi I x dot 0 0 plus e to the power 2 pi I x dot 1, sorry, and there should be a 2 1. Fine. Now this one is 0, that means 0 plus e to the power 2 pi I x by 2 1. Now if value of x is 0, then what will happen? It will 1 by root 2 0 plus x is 0. That means this expression goes to 1. This one, I think you got some similarities. You get some idea what will be the 1 qubit Fourier transformation. If x is equal to 1, then this expression becomes 1 by root 2 0 plus e to the power pi I 1. And what is the value of e to the power pi I? Very easily, 1 by root 2 0 minus 1. So 1 qubit Fourier transform is very easy. What is that? It is nothing but a Hadamard gate. If we want to design a 1 qubit Fourier transform, it will be the Fourier transform circuit. It will be the only a Hadamard gate. That's why this, for the 1 qubit case, this plus minus basis is called a Fourier basis. That's why I spend time to say what is this X basis and computational basis. Okay. So this is the 1 qubit case, but this is not a generalized case. If I say, okay, I have a 3 or 4 qubit, just I put Hadamard, and there is Hadamard and Hadamard, it become a Fourier basis. No, expression is not saying like that. For 1 qubit gate, it's very straightforward, but not a general case for the case of this computational basis corresponding to a plus plus, plus minus, and minus plus is not a Fourier basis corresponding to this 4 computational basis. So we need to, if we want to make a generalized QFT circuit, we need to do more. So again, I'm writing again this expression x dashed QFT of x. Very first I'm writing root over n and there will be y. So if it is our 4 qubit case, then what will be the expression? 1 by root over 2 to the power 4, and y0 comes from 0 to 15, and e to the power 2 pi I xy by n and y. See, here y value goes from 0 to 15, 0, 1, 2, 3, 4, 5. But quantum computer or any your classical computer, it should be, y should be either 0 or 1, or any other, in case of qubit, there will be the 0, 1 state or plus minus state should be there. But there is no concept of decimal representation directly in quantum computer. So from this expression, we can't design a quantum circuit. Again, we need to do something and try to do this. So if I write y as a y1, y2, and yn, what is that? This one is a decimal representation, binary representation of this decimal. So we can generalize this expression as like 2 to the power n minus 1. Suppose yeah, y1 plus 2 to the power n minus 2 y2 plus not dot 2 to the power 0 yn. There is a general expression to converting any decimal number to binary representation. So can we frame this expression in generalize? We can generalize it like that: k equal to k equal to 1 to small n, and we can write 2 to the power n minus k by k. Now we can transfer this binary representation to this equation. What will be this equation? 1 by root over n y equal to 0 to n minus 1. There is a to the power 2 pi x. Now n can be 2 to the power n, and y can be replaced by summation of k equal to 1 to n 2 to the power n minus k yk. And here the binary representation y1, y2, yn. So do some computation over there. This 2 to the power n, if we shift there, then e to the power 2 pi I x k equal to 1 to n. Obviously that will be the cancel out, and yk by 2 to the power k, and y1, y2, yn. So this is our expression. And exponential to the power summation can be written as a product of sum. So we can write to 0 n minus 1 product k equal to 1 to n e to the power 2 pi x yk by 2 to the power, or we can say 2 to the power k here there, y1, y2, yn. Now we are very closer to design a quantum circuit. Still, we have some observation. How can we handle this summation? Product we can summation implement as a tensor between this product form. But how can we handle this summation? And still, this one is in the form of decimal, 0 to n minus 1, 0 to 15, or 0 to 16. But we can represent this expression in this way, like what is that meaning of this 0 to n minus 1? If I think about this one is 1 qubit to another qubit and n number of qubit, each and every one is qubit here. So qubit have a two state, either 0, either 1. In general, not a superposition case I'm saying, but qubit had two basis state. In terms of basis, there could be a two state 0, 1, and this also a 0, 1 and something. So we can break this expression like this way: v1 0 to 1 summation y2 0 to 1 summation y3 0 to 1 dot dot yn 0 to 1. So if I break this expression, and this one is qubit by qubit, so for 1 qubit this one is, and there is a form of product terms. Okay, so we can write now this expression in this way: 1 by root over n. So for first qubit we can write qubit can be a 0, 1, 0 and 1 state, so it will be the 0 y equal to 0 case, and if I put there y equal to 0, it will be the vanished terms, this first term will be not there. Now plus e to the power 2 pi I x. Now k is 1 for first qubit, so that will be the 2 to the power 1, and y value is 1, that's why yk is vanish, and this one y1 will come like this. Now there is a product form, so we can put that tensor. Second term will be 0 plus e to the power 2 pi x by 2 to the power 2 k equal to 2, and here y2 value is 0 and 1, it's come. So tensor in this way we can write 0 plus a to the power 2 pi I x 2 to the power n 1. Now it becomes more closer to make a quantum circuit. From this expression you can very easily design a 1 qubit. You can map. What is 1 qubit case? Our Hadamard. See, in case of 1 qubit, all of this term is not there, only this term is there. Fine. And again, I forgot to another mention what is the meaning of x. So write the full expression first, then I will tell you. So there is a x prime QFT of x. What is x? Decimal form of this x is x1, x2, dot xn. And what is that meaning? Actually, that means x1 tensor with x2 tensor with dot dot tensor xn. And corresponding expression is 1 by root over n 0 pi I. This is come from for x1. 1 tensor 0 plus e to the power 2 pi I x2 by 2 square 1, and lastly come pi I xn by 2 to the power n 1. This is the expression. So very easily 1 qubit case is that if x1 is 0, then 0 plus 1, 1 by root 2, and if x1 is 1, then 0 minus 1. So, and rest term will not be there because 1 qubit case. But from this, still we are able to design very efficiently 1 qubit get 1 qubit Fourier transformation. And for the still I need to give you some observation from this expression so that you can very easily design n qubit QFT. So what is this observation? See, if I multiply each and every, then we can get a very good terms, some of these terms, and they have some good observation. What is that? We will get a number of zero terms if we add this. See, with this n number of zero terms, there will be no phase term. Fine. And if we changes just single bit, then there will be comes a one phase term, and it will come it to the power 2 pi. I'm writing x1, not x1 x2. I'm writing directly x 2 to the power n. If I shift it one zero terms, you will get over 2 pi x to n minus 1 terms. So according to the presence of 1, actually our phase terms will changes. If you go one by one, you will get n minus 1, n minus 2, n minus 3 in this way. And another terms you will find that is totally 1, 1, 1 in terms. Here you will get all the summation of this each and every to the power 2 pi I x by 2 to the power n plus, I'm right, this is add up of this exponential, that's why I'm adding to the power 2 pi I x by 2 to the power n minus 1, and this way it will 2 pi I x by 2. You will get these terms as a phase terms of where all ones present. And combination of 1, 1, that means it will give you the two different terms. Let's take another example. If we want to make a 2 qubit, 2 qubit Fourier transformation. Then there will be these two terms only. So example case, there will be a 2 qubit Fourier transform. So 2 qubit means 2 to the power 2, that 4 terms will be there, and 2 to the power 2, and that means half. I'm writing this expression in terms of this example. So there will be a 0 plus e to the power 2 pi I. I'm not writing x1, x2 because according to x value, it will be 0 or 1. So I'm directly writing x to 1 tensor with 0 plus e to the power 2 pi x by 2 to the power 2, 1. Now you can easily compute this. I overlook about the normalization term. If I forgot to mention, don't mind. So 0, 0. Now 0, 1 is e to the power 2 pi x by 2 to the power 2, 0, 1. See, this is 0, 0, 0, 1. So for changing 1, 1, it will 2 to the power n. Now n is 2. That's why it's come 2 to the power 2 from this expression. Now plus here 1, 0. E to the power 2 pi I x by 2, 0. Oh, sorry, 1, 0. And see, 1, 0, it's come n minus 1. So 2 minus 1, it is 2. Now, if we do 1, 1, then here comes addition of this two term, e to the power 2 pi I x by 2 plus 2 pi I x by 2 to the power 2, 1, 1. So as per the terms, this is from this example case, you will find this. So from here, how can we design a 2 qubit QFT case? We need definitely we need a Hadamard case for one ingredient is Hadamard, and another ingredients we have required a U rotation, U rot K. What is that? If we apply U rot K over any operator, maybe XP, then it will return 2 pi I xp by 2 to the power k of xp. You don't need to mention here this xp. This one is xp. According to 0 or 1, it will come. So if it is a 0 state, it will vanish, and if it is a 1, okay, better to write this, otherwise it will be misleading. XP there and XP. So what is the matrix of this U rot? You know, if it is x0 equal to, it is a 0 because this term will vanish. So 0, 1, 0 and 0 e to the power 2 pi I 2 to the power k. See, according to the position of bit, we need to give this value of k to our quantum circuit. So what will be the 2 qubit QFT circuit? There will be, this one is x1, x2, and we need a control unitary because we need to give this phase according to position of 1 of x2. That's why I told you the phase kickback is required, because we need to shift this phase to our control state. That's why we have required here, sorry, that will be the control, this one unitary, U rot, I'm say U rot. And what will be the value of k? Value of k will be your x2, that's why k of value is 2. This part is for first things. And for x2, this is a single qubit, and single qubit we require only Hadamard gate. That will be the your 2-qubit Fourier transformation. Is there any question? Because I say a lot of things within this limited time. How can I make this QFT circuit from this expression? Is there any question? Or it is a heavy mathematical? Hello.
Yes, you can wait because students are getting, but still they are shy to ask question.
Okay. So this one is our 2-qubit QFT. So from this intuition, you can build up your n qubit. Just I'm giving the intuition. After doing computation, you can generate in yourself. Just I'm giving the intuition. X1, X2, that is Xn. So n qubit will be the Hadamard, and you have to put a I'm say R for rotation gate, and it will come from this control, and k value will be here too. And also we have to put, suppose there is another line, you have to give another rotation R, and here if it is x3, then rotation k value will be 3. In this way R, there will be the n. There is a dot form, there is more and more gate. And again we have to start for the case of second qubit, and you have to give, there is a again control rotation. It's come from 3 minus 1 in minus 1, so it will be the again 2, and here rotation will be n minus 1. In this way you can design your n qubit, and now you can very easily understand why I am putting all of this control not over for x1, because see, all one case we need to add up the all phases coming from the others qubit. That's why I need to give this u rotation. Okay. So from my first part, I have finished this portion. So if you have any question from your side, you can do it. Then if you have no any question, then I can stop here and I go change my device to show you the Qiskit circuit for basic preliminary.
So please go ahead.
Okay, thanks.
Munju madam, do you have any question? I think
Sir,
you were trying to ask them.
yeah, actually, I'll try it to
Okay.
ask at the end. So actually, I want the reference of this complete in the single flow because we have all the bits and pieces in many materials.
Mm-hmm.
So if it can you give us a reference for the same?
For this total derivation, I think you will not find somewhere. I can share my documents,
Yeah,
and
sir.
I will share this because in Qiskit, like no, you will not find total
No,
expression
I
wise one by
tried
one.
everywhere. Yes.
Yeah,
I
no,
mean,
you will
this
not
all
find.
the things are bits and pieces in every book, but like different places different. So I wanted
Yeah,
to know
yeah, yeah, yeah.
what is in single.
So I can send this. I can
Yeah.
send this
Thank
total
you, sir.
expression. I will make a
Thanks, sir.
good notes because
Yeah.
here handwritten is very bad. So I make a good
No.
notes and I can send it.
But even this also we wanted, sir. I request.
Okay.
Yeah.
Okay,
Thank
sure,
you.
sure. I'll send
Yeah.
this. I'll
Yeah.
send it.
Thank you.
Sir,
Okay.
you just share your all the resources, whatever you are having.
Hmm.
I will share with all the participants. Okay, sir.
Okay, sure. I'll send. So I need to disconnect from here. I will connect. Give me a 1 minute. Okay.
Yes, sir. Yes, sir. Please.
Okay. Thanks. Am I audible? Hello? Hello?
Yes, sir. You can go ahead.
Okay. Okay. First of all, if you want to do any computing in IBM Cloud, so you need IBM Cloud account, IBM Q login account. I have already account, that's why I enter. And if you go to this home, I'm showing you. You will get this type of skin. Here you will find so many learning materials and tutorials from this IBM Q site. All of these are free. Okay, and there are another tools to do quantum computing. This is called Composer. By using this Composer, you can graphically design your circuit like this way. But I will not describe this. This is not good for the as a computer science guy, because this one is for a school student. They can be habituated with quantum computer, because IBM have one motivation to transfer knowledge up to the skill knowledge to the school level. That's why they have designed this Composer. But you can't do lot things in by using this Composer. Okay. So there is another tab. This is called Lab. From this you can write your code. And before directly going to the code, because within this time, within this small time, I'm not able to write the code. So previously I write some sample code. I'll show you this. So first, I'm talking about the basic circuit design. Okay. First of all, this one is very user-friendly cloud platform. So if you enter into this cloud, it is automatically will say how can you create a folder in this cloud, and then how can you create a new file within this folder. You'll direct it, and then you will get a IPUNB file, Jupyter notebook. And see, in Qiskit, actually there is a you can design a quantum circuit. Quantum circuit has two components. Quantum circuit is a class in Python library of Qiskit. So quantum circuit has a class as a two component. One is quantum register, and quantum register is also another class. Okay. And another component is classical register. This is also another class in Qiskit library. So if you want to make this quantum circuit, you need to import it from Qiskit. That's why I have from import Qiskit. If you are familiar with Python, then very easily you can import the quantum circuit class here. Now, if you want to building a circuit, and this tutorial you will find very easily in Qiskit live Qiskit tutorial. I'm also following this thing. It will be better for future reference. That's why I'm not giving the new things. I will show you some new things in later, but initially I describing from the Qiskit textbook library, so that in further you can also modify these textbooks text for your purpose, to your learning purpose. That's why. Okay. So there is a case after importing this quantum circuit. Now, if you want to create a quantum circuit, so there is a parameter 3. If I put this 3 parameter, that means I want to create a 3 qubit quantum circuit. If I put there 1, that means I want to create a 1 qubit quantum circuit. Just like, okay, sorry, I'm not executing first step. Okay, fine. So I have created a 1 qubit circuit. If you print it or draw this circuit, what will you get? Draw. And if you want to draw in MATLAB, MPL drawing, sorry, CRC. Yeah, there is a only single qubit register there. Nothing gate I have added there. So this is a single qubit circuit like this. Now, if I want to put one gate over there, suppose I want to put X gate. So where I want to put, I have a single qubit circuit now, and here indexing will start from 0. That's why I want to put this X on 0th qubit. Now if I draw this, we'll get a X gate over there. So if you want to change it to a Hadamard gate, sorry, then it will give you again Hadamard. Okay. If I put over there a 2 qubit quantum circuit, just I change there and see. And second qubit, I didn't paste any gate. That's why it's look like this quantum circuit. Next, I want to show because I have already told you that if you want to get outcomes as a deterministic outcome, we need to measure the quantum state. So we need a measurement operator so that actually measurement operator gives you the expectation value. And again, I'm using one term, expectation value. Don't think it's a huge term. It's a simple things. Actually, we will do in our product and something like that. I'm not going to the any mathematical. So, if you want to
Sorry, sir, your voice is not coming.
my voice is not coming. Oh,
Yeah, it's fine now.
okay. Yeah. So just a minute. Now clear na voice.
Yes, sir.
Hello. Yeah. Okay. So if you want to do the measurement operator, and after this measurement, there is no quantum state. So result will be in a classical. So we need a classical register to put this. And here, if we do 3 dot measure all, now see, this is your quantum circuit. Measure all means this measurement gets after this measurement result will go to the mesh register. Mesh register is our classical register. That's why I told you that quantum circuit has a two component. One is quantum register. This Q0 and Q1 is our quantum register, and mesh is our classical register. And after this measurement, first qubit result goes here to 2 qubit. That's why there is a 2 measurement line is there. First qubit measurement line with map with a first classical register and second qubit measurement. In physically, what is happening in physical computer? Qubit present in a refrigerator and our resonator, this toolbox is outside this, and we never disturb this quantum state. Why? Again, here comes another question. See, Quantum measurement is probabilistic measurement. So one shot measurement can't give you the actual observation. You need more and more measurement. What does that mean? If we measure the refrigerator qubit or this anharmonic oscillator in physically, if we measure, that means we destroy this qubit state, and this one is for first shot. Suppose you want to do the 1000 shot, then again you need to prepare this anomet and again shot, again need to prepare and again shot. So thousands time you have to create this Hadamard gate, but creating the Hadamard gate in a same way by sending this pulse to this refrigerator qubit, it's not a easiest task, because after 15 or 16 measurement, and this pulse may be decayed on something like that, so error may comes. That's why we didn't disturb in physically this qubit. This qubit state is holding, and there is a coupling things exist in a resonator, or it's called a cavity. We actually measure this cavity. Actually, if any changes in qubit state, that is reflected by phase transformation in a cavity. For viewing this cavity, actually we measure this cavity 1000 times or so, yes, and we bring up this result. Okay. We never disturb in physical way. So don't think that yeah, here measurement 1000 time measurement meaning we are making a quantum circuit 1000 time and 1000 and measure it, destroy it and measure it. This is not like that. Okay. So next, we want to create a quantum circuit of GIZ gate. This one is very famous operator. So I follow this same thing. That's why I stop. I just commented out this, and I again put it there 3 qubit. Now this one is 3 qubit case. And for making this circuit, we need a Hadamard gate and CX gate from 1 by 1. That's why I put there. That's why actually this is a very simple circuit. So you can work out your hand to how can you design this quantum circuit, because this root over 2 terms, by viewing this root over terms, you can immediately understand there should be a Hadamard gate. That's why we have required a Hadamard gate. Now you need to transfer. Hadamard gate gives you 0 and 1. Rest of the state are 0 0. So we need to modify it according to that. That's why you have required a CX gate. So we have created. Now if I draw this circuit, already tested, this one is our GZ gate, and if you execute this, it will generate this state. Now how can you see the result? Okay, that is a simulator. So Qiskit provide you 3 types of simulator. One is called a state vector simulator. Actually, state vector simulator is a exact solution. It will give you the it not required any measurement. We don't put any measurement over there. We want to see the what is the quantum state simulator in simulator. That's why by using state vector simulator we can and check this what is the state. So if you execute this, it will generate the same state. Sorry, this one is 00111 state. Okay, and there is another way to represent this. This is called array to latex. You will find this. Okay. And you can also view in a block sphere, and better to say this one is called a Q sphere. Q sphere, and there is a difference between block sphere and Q sphere is that block sphere you can view the phase of your qubit state, but in Q sphere you can they visualize the phase by using the different color combination. You can try it out with a different number of states so that it can give you the different color space. Here nothing to show. This one is our case. Next, we can also print hint on plot. Here from this plot, there is a two different part. It will show you. I'm not executing because this part will give you the real part, and this one is your imaginary part of the state. See, in our state there is no imaginary part. That's why all things are black, and real part there exists only 000 and 11. That's why this 000 space is white and 11 space is white. Okay. This is another kind of representation we have required for analyze our quantum set in different time. And another things, suppose there this state vector simulator gives you the outcomes of quantum state after computation from the initial state to this final state. What will be the final state? You can check by state vector. But if you want to check the what is the matrix of this total operator, this one is as a operator. This one is our initial state. We apply this quantum operator. Here quantum operator is successive operation of Hadamard, then C naught, then C naught between this two angle. So it will be the another unitary operator. So you can also check this unitary operator by using Qiskit runtime info. This one is package where operator is there, and if you call this operator and pass as an argument of your circuit, then you get the unitary, and you will get this unitary matrix. You can view it. Next come another simulator. This is called chasm. Chasm simulator is give you the real feelings of quantum hardware execution, but chasm is also a simulator. There is no, this is not a real backend simulator. This one is also noiseless simulator. It will not give you the any noisy environment or real feelings, but it's a mimic of the errorless quantum computer. So by using chasm simulator, you need to put the measurement gate, otherwise you will not get outcomes, because state vector gives you the state of the final state of this quantum computer, but before the measurement, this state we can't understand because it's a probabilistic state. We that's why we simulate this state, and after measurement we try to match it, what is the error and what is it exactly coming out, or is there any error. And chasm simulator also gives you the measurement, and it gives you the probabilistic outcome result in a in human readable format. That's why, see, here we are designing a quantum circuit, and there is a 3 qubit and just three classical register. In this way, you can also design. Also, you can design here. Just put there is a quantum circuit, and if you put measure all, it's the same outcomes. But I want to show different way. You can also do this. I'm creating another quantum circuit. This is called there is a 3 qubit and 3 classical register, and I'm putting this here barrier means segregating the quantum state with the classical measurement state. Now measure from where to where. This one is from quantum state to classical register, quantum register to classical register. And if you draw this, actually, oh, sorry, I am taking more time. I will take only 2 minutes. Okay. And now, if you there is another things. You take that this one is designed. Now we need to execute in a chasm simulator. Just for doing this, we need a transpile actually transpile your logic level circuit to a physical level interpretation. That's why after this transpilation, this quantum circuit transfers into a pulse level simulation, pulse level, and then it goes to the real hardware. But here we are not putting real hardware. Air simulator is actually our chasm simulator. That's why we are putting there is backend. If you want to execute in a real hardware, then you have to put the backend name there. Now you after this compilation, we generate another compiled circuit. Now we are putting there 1000 number of shots to this circuit, and after doing this, if we want to print the result, you have required a get counts. Counts gives you the what will be the final outcomes. This is the final outcomes. Now if you want to plot this in histogram, it will give you the histogram, and you don't have to remember where is this plot histogram. Actually, it is in Qiskit visualization package. So this is the things. I'll not go to the transpilation process. It will take another time. Uh, if you have 1 or 2 minutes, then I can show you another things. Okay. Here I want to show different optimization technique. So transpiler do lot of things, a lot and lots of things, and that's why I want to show this. May I take just 3 or 4 minutes? I will take. So I'm creating a 2-qubit circuit, right? And I want to create a very simple circuit. This is called a normal Bell-state circuit, and I'm going to do execute in air simulator. Here we can also put optimization level. Now I'm putting optimization level as 0, and I'm drawing this circuit. See, from this here you can get a depth of the circuit as well as number of gate is there count. You will get, see, there is 2 measurement gate, 1 Hadamard gate, and 1 CX gate. There is no need to, and again if we do outcomes like that. Now I want to change this circuit. I'm putting there another CX 0, 1. And draw. I'm putting 2 CX gate, and see, unitary and the CNOT gate is commutative gate. So this, if I apply 2 CNOT gate simultaneously, that means it's an identity. It's doing nothing. Okay. So again simulation. Still, I'm doing the optimization level 0. So circuit is same. There is no optimization, and see, here yours 2 number of CX gate and 2 measurement, 1 Hadamard gate. Outcomes will changes because there is this is identity. Now, if we change this optimization level to 3, then what will happen? See, it vanishes this 2 CNOT gate, because this do not get we no need to execute because they are identity. So by using this optimization, if you do this in Qiskit, there is 3 optimization: 0, 1, 2, and 3. 0 optimization level means quantum compiler, this transpiler can optimize your circuit. 1 means it's just checking the is there any identity. Yeah, it will be the same. If I put there 1 optimization level, your circuit will be changed same. Okay, if I put there 1, similar like it will work as optimization level 3 and 2, but in the each and every step they do different kind of optimization. In case of optimization level 1, they checks only identity. In optimization, their circuit to a graph, and then try to make some isomorphism graph, then they find some identity and optimize this way. And in optimization level 3, they use a ZX calc. Okay, by using this ZX calculus, they optimize it. And from here, you can see it's the same things. There is no measurement, no CX gate, and outcomes will be the same. Okay. Last 1 minute I will take. And now, suppose if you want to get a real feeling in simulation environment to the noisy execution or noisy circuit, if you want to check what is the noise level of your device backend in simulation environment, because sometimes if you go to the real hardware, there is a very long queue. You can test your, if you want to test your circuit in a device, you have to stay for a 1 or 2 hours. Sometimes you can be a 1 day wait. But if you want to test locally in noisy and real feelings of real hardware, then you can make a noise environment, so that you have required a Qiskit runtime service. Qiskit runtime service is quite different from your normal Qiskit service, because Qiskit runtime service give you the two primitive. One is sampler, another one is estimator. If you want to get an expectation value, then use estimator. If you want to get the probability outcome, then you have to use sampler. Yes, and Qiskit runtime environment is actually optimized where they put your circuit into the classical and quantum computer, because if you have, VQ circuit, it requires a classical computer as well as quantum computer. So Qiskit runtime circuit, it's optimized way do this. Just I want to show. I will take 1 minute more. Okay, then this is, now I am creating a backend as a IBM Chasm simulator, but device backend I am taking fake Cairo. This is a noisy fake device, not a real hardware. I am creating this backend, and also try to make a noise model from this Cairo in fake Cairo. So yeah. See, here is option, means option class. By using this option class, we pass the a different option to our Qiskit runtime service. That's why how many number of shots I am thinking 1,000. Optimization level I am using 0, and resilience level means I want to do mitigate our noise or not. Here I am not using any noise mitigation scheme. That's why now this one is my in circuit. Now I'm creating Qiskit runtime environment. See here in this option, I'm not putting any noisy backend. So here our backend is, see, here backend is simulator, not a device backend simulator. So there is a ideal simulation environment I'm creating, and you will get a result of this circuit and plot this histogram. It's the ideal simulation histogram plot. It will plot. And in second, I am creating another options where I am using a device backend as a backend noise model. And they see there is the ideal simulation of 00 and 11. It's coming, but here I am taking a noise model from the Cairo backend noise model. So if I execute same circuit, see, circuit is our QC. In previous case also QC. If I execute it here, will get a different outcomes. See, ideal outcomes is 0011 for the circuit, but if I execute in a noisy environment, just after execution, you will see, just yeah, uh, there is also other terms is come, not only the 0011, there is coming 10 and 11 as 01 as a noise outcome. This is the feelings of executing in a real hardware. Okay. That's all from my side. I take more than 13 minutes. I'm really sorry. Yeah, you will get this for the same circuit in noisy environment. Okay, I'm stop sharing.
Any questions from the audience? Hello, Sudhindo. Actually, I am
Yeah.
Sumant. So actually, I am the other coordinator. So Actually,
Okay.
so he has gone
Fine.
to some personal work. So I'm
Yeah, yeah,
taking
yeah,
charge
yeah.
of that. Okay.
No issue.
So
Actually, I take more than 13 minutes. I'm really sorry. Really sorry for that.
actually, any questions from the audience? Anybody has some question?
No,
I
sir, the
have some
session was
questions.
very informative, sir.
Yes.
Thanks.
Ask questions. Anybody have any questions? So I have some questions, few questions. Okay.
Yeah, yeah,
Uh,
yeah, yeah.
so I've heard about Qiskit for few last some days. I have heard.
Mhm.
So this Qiskit simulation, which was showing that you are optimizing the thing, optimization, different levels of optimization. So what is it optimized? Is it optimizing delay or
Mhm.
or the area or power? What kind of optimization it is?
Okay. Yeah, in transpilation level, there is some optimization means suppose you have a circuit. When we suppose I have a mathematical expression, I constitute the circuit for this mathematical expression, and in this logic level, there are so many gates there exist. In naked eye, we can't find the identity over there. There may be some identity exist. So, and
Okay.
if our circuit depth is very high, that means our quantum qubits, all the qubits will be stay in a long time in this execution path. So qubit it will start decohering, and you will get more and more noisy outcome. So our actual our goal is to reduce the depth of the circuit so that we can finish our tasks within the gate fidelity or decoherence within the decoherence time of our qubit. So
Okay.
we use this different optimization level, and there is so many behind logic for optimizing this. In optimization level, the Qiskit do transpile aggressively optimization for by using ZX calculus mostly. They use.
Okay, so there is a lot of challenges also in designing these compilers also, I think.
Yeah, yeah, yeah. Really, it's
Actually, I
challenging to
still
design.
the compilers, so that's why I am asking these questions actually.
Okay.
Mm, Okay. So thank you, thanks a lot
Thanks.
for your valuable talk. Okay, so are there any questions from the audience?
Sir, actually, myself, Sanjay Mukherjee, I'm driving, but still I have some queries, if you don't mind.
Okay, okay.
So actually, like in classical computers, if you go to the gate level for constructing any kind of circuit component, so we must consider the clocks, okay, and
Yes.
synchronization. So is there any question about
Yes.
synchronization here?
Yeah, actually, each and every qubit there is a frequency of the qubit, and so qubit are connected. Some qubit there is no isolated qubit because coupling qubit is there each and everything, and so if you have a all qubit at same frequency, there may be a chance to interference between to that. That's why we have at each and every qubit with a different frequency, and we need to tune this frequency, and each and every qubit has some t state. This qubit can exist up to this t state decoherence level and something. If it is exit, then it start decohering. So we need to think about also that t state level or frequency level thinking, not like the clock of things. Okay. Similar like
Okay.
of this, there is some t state and frequency tuning. Actually, this is done by Qiskit pulse level programming in
Okay.
low level programming.
Sir, one more question. So
Okay.
when you're talking about two types of running the circuits, we are having two options. One is the real hardware or the simulator like chasm
Yes.
simulator kind of
Mm-hmm.
thing. Okay.
Mm-hmm.
So when we are running my circuit on
Mm-hmm.
IBM cloud, like actual hardware, okay.
Mm-hmm.
So there are many people simultaneously supposed to trying. So how
Mm-hmm.
this thing actually being handled, like this hardware being allotted to the different circuit. Yeah. So how actually it's
There is a
being?
there is a
Yes, yes.
sequential execution. If I suppose we are 5 people, we are giving this job. There is a scheduler choose one by one, and they executed one by one these circuits. Okay. If it is a small circuit, then they can put a same computer 2 or more circuits in a different enough by using the enough gut, but still not this type of reach scheduler is there, but still it is a sequential. But there is some weightage. Suppose your circuit is very lighter, then they gives a very first chance to execute in real hardware. Or there is some payment mode also there. If you're a paid customer, then obviously there will be a no queue for that case. And yeah, suppose there is a more than 2 or 3 paid customer, then there also have some queue in IBM cloud. It's a complete
Okay,
sequential
sir. Thank you
execution there.
for the answer. Sumant sir, please you carry on.
Okay, so thank you for your valuable lecture, sir, and thank you audience for joining this program. Okay, so today we are finishing today's day 4 is finishing. So tomorrow we will start again at then the first half 10:30. So Manish Madani will be speaking on Dr. Manish Madani will be speaking on NVIDIA on high performance computing and quantum simulation acceleration. Okay, and in the second half from 2:30 p.m. onwards, Dr. Anshul Saxena will be speaking on quantum computing in finance. Okay, so again tomorrow we will meet. Please join time so that we can have another good session tomorrow.
Okay, thank you again. I am apologize. I am taking more 20 minutes.
So I heard about quantum gates when I was in my second year. So Amran sir used to teach. Amran Chakraborty sir, professor, used to teach in my undergraduate time. So when I was learning classical logic gates, he was going to attend some conference on quantum gates. Okay, so from that I knew, but we didn't concentrate much in these things. So now again we are in things. So I will often contact you. Okay, sir,
Okay, okay.
and keep touch with you.
Bye.
Okay,
Bye.
thank you, audience. Okay, goodbye. So I'm leaving the meeting.
Bye. Bye. Bye.
So tomorrow we will again meet at 10:30.